Okay, so in the last few videos, and in the last chapter, we spent a lot of time talking about integrals, and in particular definite integrals, and different ways to solve them. In this chapter, we're going to continue that rather briefly because it's the last week of the semester. You'll go over more of this in chapter 2. But one thing I did want to stress before we go through any of this, as of right now, the main way we've used integrals is to find the area under a curve. But just understand, and I mentioned this during my Zoom session, and it's one of the things that confused me when I was a student, an integral is not the area under a curve. The area under a curve is an application of the integral. By definition, a definite integral is the limit of a Riemann sum. It just so happens that if we have some curve like this, the way we find that value is we say, oh, I'm going to approximate it with a bunch of rectangles. And then I'm going to make those rectangles get narrower and narrower and narrower. So my delta x is right here will get narrower and narrower, smaller and smaller. And then as those get narrower, this approximation of the area under the curve becomes exact. But that's all this says right here. F of x sub I is just the length of that rectangle. Delta x sub I is just the width. Which means all this literally says it's a limit of a sum of a bunch of rectangles, which happens to be what we have here, which allows us to use it to find the area under a curve. But do not assume that an integral is an area under a curve. It's not. Area under a curve is one application of the integral. I stress that because it confused me when I was a student. And as we get into more and more complex integrals this week and throughout Calc 2, if you don't understand that this is just an application of that, then it gets really confusing to think about. But in this chapter, we're going to expand on this idea of area under a curve and different ways to use the integral. We've established, if I wanted to say integrate the sine function from 0 to 2 pi, well, I could integrate from 0 to 2 pi sine x dx. And then if I integrate, the antiderivative of sine is negative cosine x, evaluated from 2 pi to 0. That's negative cosine of 2 pi minus negative cosine of 0. Cosine of 2 pi is 1, so that's negative 1. Negative negative becomes plus. Cosine of 0 is 1. I get negative 1 plus 1, which is 0. And the idea, and you did some of this kind of for homework, is that geometrically, this area right here is positive, this area right here below the axis is negative, and as it turns out, we know these are symmetric, they're the exact same. So these things cancel out, which is why I get an integral of 0. One thing we can do when working with integrals, and I stress this because it's more in how we just choose to set up problems, you can be told to find the area under the curve of this right here, and then you just integrate like normal, get an answer, and you're done. Sometimes the problem will be worded differently, and you'll be told to find the area between the curve and the x-axis. When you are solving that, what it means is you want everything to be positive. So you would say, okay, it's positive right here, so I'm good. This is negative, so I want to find this area right here, and then I'm going to take the absolute value of it and make it positive. Just understand, it's the difference between find the area under the curve and find the area between the curve and the x-axis. Again, as we get to more complex things in this chapter, understanding how the problems are worded is important. For this one then, to find the area, we don't have to do it out, but to find the area, we know that's x equal to pi. We would just integrate from 0 to pi, because that's always positive, sine x dx. Then I would add on the absolute value of the integral from pi to 2 pi of sine x dx. This will be negative. I take the absolute value as positive. And then I'll get this area plus that positive value of that area, which will give me the area between the curves. You can all solve that out, so I'm not worried about finding the value. But just be aware, because now we want to expand on this idea, this application of area under a curve, and actually go back to something you probably did in 7th grade. So suppose I have this. I'll try to color code this. F of x is x squared, and we'll say g of x is equal to x. I want to graph those. No, I have to use black for the axis so I can color code the two functions. So now I'm going to go, let's see, x squared, there's a parabola, and it looks like that. And I'm going to label, this is the point 1, 1. Now if I graph g of x equals x, I get the line that looks like that. And yes, notice between 0 and 1, the square function is below the line y equals x. Once you pass 1, the parabola gets really big, and it goes above the line. I want to find this area. The area between those two curves. And the idea is actually pretty straightforward and simple. Assuming you remember, again, like 7th grade or 8th grade. And what I mean is, in 7th grade or 8th grade, you're told, I have a rectangle or a square, and then I have a walkway around that square, or it's just a picture frame. Find the area of the picture frame. And then what's the trick? You find the total area, you find the inner area, you subtract the two, and the difference has to be the picture frame. They try to make it more advanced by maybe ultimately doing circles. Find the area of the donut. But it's actually the exact same. Find the area of the whole circle, find the area of the inner circle. The difference has to be the area of the donut right there. That principle keeps on expanding even here in calculus. Find the area between those two. But what I can do is, I can find the area underneath the line right there. That's the integral from 0 to 1 of, I'm sorry, green is g, of g of x dx. That will tell me, I don't want to scribble over this and make it too messy, that will give me this entire area. If I integrate from 0 to 1 f of x dx, that will give me the area under the red one, which now I'll color in. It'll be right here. Now if I find the difference between those two, the difference, just like the donut and the picture frame, has to be the stuff between them, which is what I want. But we understand that if I subtract these integrals, the difference of two integrals is just the integral of the difference. So I can actually rewrite this as the integral from 0 to 1 of the top function, which is x, minus the bottom function, which is x squared, dx. And now that's an easy integral. Let's see, antiderivative of x is x squared over 2, minus x squared is x cubed over 3, evaluated from 0 to 1. If I plug in 1, I get a half minus a third, minus, if I plug in 0, both of them are going to give 0. A half minus a third, that's 3/6 minus 2/6, and I get 1/6. And again, we're really not doing anything incredibly more complex. It's a basic principle that you learned in 7th grade. You find the bigger thing, you find the smaller thing, you subtract the two to get the thing between them. Only now we're doing it with different bizarre looking graphs. What it does mean though, is that you really need to graph everything you're integrating. Because you want to make sure you know which function is on top and which function is on bottom. And we can actually expand this problem. And what if I said, I wanted to find the area between those two curves as x goes from 0 to 2. Well now if that's 1, 1, let's see, this is the point 2, 2. So right here is the point 2, 4. Now the area I want is all of that. And here I'll erase this so we don't get too confused. Now I'm looking for those two things. And now, can I just take the integral from 0 to 2? Well, no, this is similar to finding the area between the curve and the x-axis that we did with sine. Now, from 0 to 1, the green is on top. From 1 to 2, the red is on top. So to find the difference between them, I have to break up my integral. And I have to integrate. I'll do it in black since all the graphs are in green. The integral from 0 to 1 of the top function, which is x, minus the bottom function, which is x squared, plus the integral from 1 to 2 of now the red function, minus the green function. And now I have to solve both integrals. If I do this really quickly, we've already done that integral right there. It's 1/6. This x squared becomes x cubed over 3 minus x squared over 2, evaluated from 2 to 1. And I get 1/6 plus, if I plug in 2, I get 8/3 minus 4/2, which is just 2, minus, if I plug in 1, I get 1/3 minus 1/2. And now that's 1/6 plus, let's see, 8/3 minus 1/3 is 7/3. Minus 2 minus 1/2 is minus 2 plus 1/2, which is minus 3/2. And now the common denominator is 6, so I get 1/6 plus 14/6 minus 9/6. 1 plus 14 is 15. 15 minus 9 is 6. And assuming my quick arithmetic is correct, I get 6 over 6, which is 1. And there we go. And again, I'll point out, the integral I know is really straightforward and simple. The trick is in making sure I graph it and making sure I understand, okay, what's on top, what's on bottom, what's on top, what's on bottom. Is there always one function on top? Is there always one function on the bottom? If there's not, if they cross over, then you have to find where they cross over and break up your integral around the crossover points. Algebraically, I'm sure you all remember, if you can't immediately see the crossover point, like here we get it at 1, you set the two functions equal to each other and solve, and that will tell you where they cross each other. But suppose we expand on this again, and now let's see. Okay, bear with me. We're going to let f of x equal x squared minus 1, and g of x equals, let's see. Just bear with me. Negative x plus negative x plus 5. Hopefully my quick graphing in my head will work here. But let's see. Graph them. So we'll go down here, and we're going to integrate starting at 0 again. And we want to go from 0 less than or equal to x less than or equal to 2. So I'm going to have to go down here, I think. X squared minus 1. At 0, I get 0 minus 1, which is minus 1. At 2, I get 4 minus 1, which is 3. And it's a parabola. It crosses the axis at 1, but I'm not really concerned with that just yet. For this one, at 0, I get 5 minus 0, which is 5. And at 2, I get 5 minus 2, which is 3, right here. And I get that right there. Now I want to find the area between them, which is all of this. And now we have one potential problem. This is above the axis, this is below the axis. And the question is, we know that if something is below the axis, then it will give me a negative integral. And do I need to somehow break this up and get an absolute value so that this is positive and that's positive, and then I do all of that. And there's actually a trick here. Suppose I take this whole picture, and one thing I can say is, well, I only care about the area between them, that shape. It doesn't actually matter geometrically where that shape is. So what I'm going to do is, all of you remember your algebraic graphing tricks from like pre-calc? I'm going to raise both graphs up 10. So all I have to do, that's not a big deal, I just take a plus 10 here and a plus 10 here. And I'm deliberately not going to combine those. But all I know is this point then will be way up here, and this graph will be way up there. It'll look the same, but everything will be above the axis. And then I can set up my integral. The red one's always on top, so it will always be the integral. X will still go from 0 to 2, and it will be the top one, negative x plus 5 plus 10 dx, minus the bottom one, I'm sorry I put the dx there, minus the bottom one, which is x squared minus 1 plus 10 dx. And again, I'm deliberately, there my cat's just jumping around again, I'm deliberately not combining the constants, because if we just manipulate this, that's the integral from 0 to 2 of negative x plus 5. Now I'm going to distribute the plus 10 minus x squared plus 1 minus 10 dx. And now right away I see plus 10 minus 10 cancels. Which means adding the plus 10 here and here didn't actually change the integral at all, because the 10s just canceled themselves out. What that means is shifting this graph up 10 to get the integral, which I know would always be positive, and I would therefore get the area I wanted, I didn't actually have to shift it up. Because shifting it up just essentially added an arbitrary constant to cancel itself out. Which means when you are finding the area between two curves like this, you do not have to account for whether one of the curves is below the axis. You always just do top minus bottom. The only thing you care about is if they cross over. In this case, if I integrated further than x equals to 2, then I would actually care about that point, because then the graphs switch and I'd have to do two integrals, one from 0 to 2, another one from 2 to whatever x I cared about. So just keep that in mind. If you're dealing with one function and you want to find the area between the curve and the axis, then you have to account for the negatives and make them positive. If you're finding the area between two curves, then all you need is top minus bottom and find points of intersection if necessary. There's actually a reason for that. They actually mean the same thing, area between two curves or the curve and the axis, up to how you look at it. I'm going to leave it up to you people to see if you can kind of ponder it and figure out what I mean by that. But in principle, it's the same thing. But just to solve this one out, I'll be right to shorten it and go without the 10s in there. I can erase this too so it's out of the way. We get the integral from 0 to 2 of the top function, which is the red one, negative x plus 5, minus the bottom function, which is x squared minus 1, dx. Which gives me, let's see, negative x squared over 2 plus 5x minus x cubed over 3 minus 1 is plus 1, which then becomes x, evaluated from 2 to 0. At 2 you get negative 2 squared, which is 4 over 2, so negative 2, plus 10, minus 8 thirds, plus 2, minus, if I plug in 0, all of those are 0, so I don't need to worry about it. Minus 2 plus 2 cancels, and I get 10 minus 8 thirds. That's 30 thirds minus 8 thirds, which is 22 thirds. And there we go. So again, as far as it goes, if you're just told to find the area under a curve, integrate starting point to ending point, be done. If you're told to find the area between a curve and the axis, graph it, find if it crosses the axis to see if it goes positive or negative, and then break up your integral and take positive absolute values of all of the places where it goes below the curve, below the axis. If you're told to find the area between two curves, graph them and find any points of intersection where they switch from one function being on top to the other function, and then break up your integral around those points. And then the last thing I would remind you, if you have something like this, make sure you do function minus function and distribute the negative correctly. Don't make little algebra mistakes like, oh, it's just the top one minus the bottom one, and then you don't distribute the negative in there. So just make sure to keep all the algebra clean, because it's going to get more and more complex with the other stuff we're doing. After this, there's only one more topic we're going to do, and it's really, really fun. I enjoy it, so look forward to doing that.